Dear students, welcome back to chemical technology. The last time we have discussed about the phosphorus industry. So coming to the next modules, we will try to discuss about the chlor-alkali industry. So in chlor-alkali industry, the name suggests the chlor and alkali. So chlor will represent the short form of the chlorine, whereas the alkali, the soda ash, the NaOH. So they will produce together in the electrolysis process or the other different processes we have. So they will be together named as chlor-alkali industry. So if we see the introduction and the uses of the chlor-alkali industry, so we have the soda ash, the caustic and the chlorine. So these are the three main products we have to learn under the chlor-alkali industry. So the soda ash, it's a sodium carbonate, caustic soda, better known as sodium hydroxide, and the chlorine gas as a Cl2. So electrolysis of the NaCl brine produces over 90% of chlorine with caustic soda. So in electrolysis process, we have the sodium chloride solution that may get from the sea, or we can have the NaCl in the solid form which we dissolve in water to get the concentrated brine. So when it electrolytes, then we get the chlorine gas at one anode, one side of electrode, and we get the caustic soda NaOH on the other side of electrode. So we will discuss this process, how to get it. Then this industry is worthy of study because of these production achievements. So first one is the quarries and transport vast quantities of limestone for soda ash, then extracts NaCl mineral from open water brine or deep wells, then process products to exceptional purity, and operates 100% indigenously, no imports required. So this is the main part of it, that we are not dependent on the other countries to fulfill the demand of the chlor-alkali products. Then works on economic tightrope shaping products such as a low price soda ash. So here you can see the lower cost product we can produce through the chlor-alkali industry. So first to discuss about the soda ash, which is sodium carbonate. So you can see over here, so is the oxygen ion, and here Na plus we can see. So Na2CO3, and the general form, the Na2CO3 is this solid form which we can grind into fine powder. If you see the properties, so it has a molecular weight of 106, then melting point of 851 degrees Celsius. It decomposes on heating. Then it is highly soluble in water, and solubility being 8.9 gram per 100 gram of water at 20 degrees centigrade. Then we have the two grades. One grade is 99% sodium carbonate, which contains 58% of Na2O as light and dense grades of granular products, whereas other is washing soda, that is Na2CO3 with hydrated form in H2O. So we have the two kinds of soda. One is the washing soda, and other one is the baking soda, which is sodium bicarbonate. So in this one we will study the washing soda, that is Na2CO3 in hydrated form. If we see the consumption of the soda ash, then it's available in high tonnage, then low cost, then it's a reasonably pure, then soluble alkali in the market. Then if you see the uses of it, the glass is the biggest industry using soda ash. So we are already familiar with the use of soda ash, where we mix with the sand and then we heat to produce the glass. Then 36% of total soda ash in further divided into 60% in bottles and 29% flat glass, then 7% fiberglass and 4% others. So here the major amount of the soda ash goes in the glass industry, where in that also 60%, which is a major part, goes in production of the bottles, glass bottles. And the remaining 64% of the soda ash used in a chemical formation, then in soap formation, where it is used for the neutralization and the making of detergents, then pulp and paper industry, in desulfurization in petroleum industry. Then we have the export, and then other miscellaneous uses of the soda ash. So there are three kind of processes for soda ash production. One is solvay or ammonia soda process. Then we have the dual process, which uses sodium carbonate and the ammonium chloride, and third one is natural soda ash from the deposits. So these two processes we will discuss in detail in further slides. If we see the solve or the ammonium soda process, so it is discovered by the solve, and it is the process, the widely used process in many countries. So if we see the overall reaction, then calcium carbonate with the reaction of the brine gives the soda ash and the calcium chloride. So this is the overall reaction, but it takes place in these many steps. So first step, it happens that calcium carbonate, it decomposes into the calcium oxide and carbon dioxide. Then the next step, we are burning coke to produce the carbon dioxide. Then calcium oxide with the water gives calcium hydroxide. Then EFG step, it will give the ammonia with water gives ammonium hydroxide with little bit evaluation of the heat. Then the carbon dioxide with hydroxyl ions gives carbonate ions, bicarbonate ions. Then carbon dioxide with water gives again carbonate ions. Then the sodium and the chlorine ions with ammonium and the carbonate gives NH4Cl and this sodium bicarbonate. Then sodium bicarbonates again decompose to give the sodium carbonate and the carbon dioxide. Then NH4Cl, like a reaction with the carbon dioxide, gives the ammonia and the CaCl2. So you can see the carbon dioxide production in the B and the C. Also you can see the carbon dioxide production in the ith step. Also in the last step we can see the ammonia evolution. So here we can recover the ammonia and the calcium in form of the calcium chloride. So here we require the calcium dioxide and ammonia to remove the impurities like calcium, magnesium from the brine. Also we require the carbon dioxide to have the reaction with the brine to give the sodium carbonate, which is soda ash. So soda ash here, so this is the we get by the decomposition of the sodium bicarbonate. So first we have to make the sodium bicarbonate, then we can decompose into the soda ash. So here we have to add the bicarbonates and the ammonium ion in this stage. So here the raw materials are the salt, the coal and the limestone. So salt will give the NaCl, that is brine solution. The coal we requires to heat and to produce the carbon dioxide, and a limestone to produce the carbon dioxide again. Then salt used as a brine, pumped from deep wells or as a crystalline salts via evaporation procedures. Then ammonia makeup in the recirculation load amounts to about 1.5 kg per ton of soda ash or greater than 99.8% recovery. If we see the quantitative requirements for this process, then if we are producing 1 ton of soda ash which contains 58% of Na2O, then we require salt in 1.55 tons, we require the limestone about 1.2 tons, then coke 0.09 tons, the high pressure steam 1.35 tons, the low pressure we require 1.6 tons, whereas ammonolysis can be about 1.5 kg, then cooling water 40 to 60 tons, the 210 kilowatt per hour will be the electric consumption, and generally the plant have capacity about 200 to 2000 tons a day. So if we see the kinetics of this one, then the reaction E to H are useful in explaining the kinetics of the precipitation reaction. So here the sodium bicarbonate will be precipitated and that will be decomposed to give the soda ash. So this reaction will give the rate determining step. Then rate controlling steps are F and G in the solvation of carbon dioxide. Then reaction must occur as shown in the order. Whichever the A to I steps are there, it should occur in the same way, so that it will reduce sodium bicarbonate and then we are decomposing to get the sodium carbonate, which is soda ash. Then NH4HCO3, that is the ammonium bicarbonate, is prepared and brine added. No precipitation of sodium bicarbonate occurs. In other words, ammonia must be absorbed in the brine first, then CO2 added. So this is the crucial step. If we have this one, then we will not get the sodium bicarbonate and in turn will not get the product. So we have to ensure that the ammonia is absorbed in the brine first and then CO2 is added, and then only we get the soda ash. So this we have to take care while producing the soda ash, and this becomes the major engineering problem to handle the ammonia as a solution to dissolve the brine solution. And we'll see the process flow diagram for the caustic ash production by the solver process. So you can see that we are taking the purified bar solution, then we require the coke and the limestone. So these are the three raw materials. So from here we put the brine solution, then here you can see the coke and limestone is added to form the CO2 over here. So what happens in ammonia tower, you can see the numbers are written over here. So they will represent what are the reaction that is taking place. So if we see the purified brine, then here the ammonation tower where the ammonia will be absorbed in the reaction F. So we'll see what are the reaction F. So here you can see the carbon dioxide and the hydroxide ion that use the bicarbonate ions, and here we get the ammonia and the water which gives the ammonium hydroxide ion. So these three things we can see happening in the ammonia tower and the carbon dioxide tower. So here the ammonia tower, the E and the F reaction that will take place. So CO2N2, they will go to the brine purifier. Then from the ammonation tower, it will go to the carbonating tower where the reaction FGH that will take place over here. So that will tell you the kinetics of the reaction. So the purified brine, then ammonia tower, and from this one, whatever the CO2 is produced, that is added over here. So you can see the CO2 by the burning of the coke and limestone, and here you can see the B and C reaction taking place. So whatever the CO2 is produced, that is compressed over here and given to the carbonation tower. And here you can see ammonia. We are feeding the ammonia from the external source and we are giving to over here. So we have already seen how to make the ammonia in the nitrogen industry. So from there we take the ammonia and we feed here, and the carbon dioxide by the burning of the coke and air we are feeding here at a very high pressure. So these are required in order to purify the brine solution, and we can remove the other impurities. Also it will lead to the reaction in these towers. Then whatever the products which are forming over here, that will go, which are drying in the rotary filter where the soda ash and the water solution or the filtrate that will be filtered. Then we are sending it to the calciner where the NH2O3 whichever it is formed here, that will be decomposed to give the soda ash, and then we are adding water and then we are cooling over here and it is dried and we can send them as a soda ash. And whatever the other gases that are sent out and whatever the heat which is producing over here, that we are recovering back. So you can see the first one is reaction with the ammonia and the carbon dioxide, and then we are getting the bicarbonate which we are decalcining to have the soda ash over here. And whatever the ammonia and the water which we are getting over here, so here you can see it is heated up to recover the ammonia. Also whatever the combined ammonia here, that we are recovering. And then here we are sending the milk of line here to recover the waste such as the CaCl2 or other impurities. So this will be recovered from here and the ammonia will be recovered from here, and we can have the makeup ammonia or whatever the ammonia which is recovered, we can recycle them over here, or if the ammonia is lost over here, we can have the makeup ammonia. So in other way, if we take the process in short, then purified bio solution, the water the reaction which I discussed earlier, that will be produced over here and we can get the soda ash, and the ammonia which is required here, which is again recycled back in the ammonation tower. So in this one, what are the major engineering problems? So here the development of suitable calcining equipment. So here the NH2O3 we are calcining, also the calcium carbonate we are calcining over here. So it is required to calcine them in a proper, so that it won't create a problem in filtering. So the calcination is proper, then it won't affect the filtration problem in the next stage. Also we have to see the economic balance over the tower design. So tower design, there are two problems. One is the tower height, another is the carbon dioxide pressure. So if we see the tower height, then if we increase the tower height, obviously the cost will be increased. But at the same time, if we are increasing the tower height, the NaCl losses will be minimum. So we have to take the optimum point of the. So this point where it satisfies both the things, so this will be the optimum point, and we can operate the plant on this tower height, and we can minimize the NaCl losses up to this point. Then the same way, the carbon dioxide pressure, If you are increasing the pressure in order to have the more product, it will increase the pumping cost, so we have to bear the cost for it. But at the same time, if the pressure is very high, the NaCl losses will be low. So in the same way, we have to go for the optimum point, and we can operate the point at this the CO2 pressure. So the tower height and the CO2 pressure we have to manage from the optimum solution. Then the ammonia recovery. So the major part of this is ammonia recovery, because the ammonia is expensive than the soda ash. So it's better to have the ammonia recovery equipments where it can recover ammonia in a large quantity, and that we can use again and again to recirculate in the tower and to get the product. Then plant modernization is needed in order to have the more products in a more purified quantity. And we have seen the CSL2 and the other products as a waste disposal. So we have to find either their end uses, or we can directly send them for the disposal in a proper way. So the next process for soda ash production is the dual process, or we can say it's a modified solvent. So earlier we have taken the ammonia as a solution to dissolve it, but here rather than ammonia we are using NH4Cl for the steps. So the same steps will be followed over here, that coke is burnt to form the carbon dioxide, then ammonia dissolved in water which gives the liquor ammonia, then carbon dioxide combining with hydroxyl ions gives the bicarbonate ions, then the ions they combine to give the ammonium chloride and sodium bicarbonate, which we can calcine to get the soda ash. So here only difference is, instead of ammonia we are using the NH4Cl. So here if you see the raw material will be either bland solution of higher concentration, or will have the crystalline salt. Then we have the fuel for burning and the ammonia, since NH4Cl is a co-product. So earlier the ammonia, now we are using the NH4Cl, so that ammonia is converted into the NH4Cl in the reactions, and that can be recovered as the co-product. So earlier the ammonia recovery, it was the major engineering problem. So here the ammonium chloride that we are recovering as a co-product, which also have the economic value. So if we are producing 1 ton of soda ash which contains 58% of Na2O, then we require this salt in 1.26 tons, then ammonia 0.32 tons, then high pressure steam which is 1.35 tons, then low pressure steam 0.1 ton, cooling water 50 to 80 tons, electric power we require 450 tons, then the co-product, that is NH4Cl we are getting, and earlier we are getting NH3 in Solvay, so here we are getting NH4Cl, so we get the 0.62 tons of ammonium chloride if we are getting 1 ton of Na2CO3, and then plant capacity will vary from 30 to 500 tons a day. So here we will see what is the difference in Solvay and the modified Solvay. So here the principal modification for NH4Cl recovery. So earlier we are using the ammonia, now we will use the NH4Cl, and that will be recovered as the co-product. So the earlier the NH3 that we are heating to recover the ammonia, so now instead of recovering ammonia we will have the NH4Cl as a co-product. The liquor from the bicarbonate filter is mixed with and wash salt filled to aid in precipitation of the NH4Cl, which is crystallized in a refrigerated tank continuous unit at 0 degrees Celsius. So this is the things we do to get the NH4Cl as a co-product. Then slurry is centrifuge and the NH4Cl crystals are dried in a rotary drum, hot air dryer, then packaged in bags for shipping. So here we are centrifuging this slurry, then NH4Cl we are getting, which we are drying in rotary drum, hot air dryer, and then we are packaging in bags for the shipping. So it is also have the economic value. So instead of getting NH3 and the problem associated with that we can take care of by converting ammonia into the ammonium chloride, which is also have the economic value, and that we recover and we can ship them. So this is the only difference becomes in the PFD, that the earlier process flow diagram, whatever the ammonia, so instead of that ammonia we can have the NH4Cl as the end product. Then here also the major problems become the salt purification, where we have to remove the impurities in the solution. Then corrosion, the ammonia is the corrosive agent, then NH4Cl also is the corrosive agent. So that for that one we have to choose the MOC of the required grade. And the refrigeration. So here we require the refrigeration, as we discussed that NH4Cl we are recovering back at 0 degree Celsius. So we have to bear the cost for the refrigeration. So this becomes the major engineering problems in soda ash production by the modified solvent process. If we see the economics of the soda ash, then soda ash is still the cheapest alkali, but competition from NH3 for weak alkali requirements can be expected as NH3 cost continue to drop relative to soda ash. Then price reduction can be done by increasing plant capacity. So more the plant capacity, more is the production. Then plant location factors. So as raw materials are limestone, brine solution and coal, brine sources are the key factor, being less distributed than the others. So here we require the coal, limestone and the brine. So the coal and the limestone we can have in the quantity, but the brine solution, as the sources are limited, so always we have to look for the plant where we can get the brine sources available in major quantity and the nearest to the plant. So the brine sources that will affect the plant location. An industry diversification needed to use available brine wholly for the production. So here if we are looking, as the brine sources are the key factor for the plant location, so we have to go for the processes where they produce the products by the utilization of brine. So here it may be the soda ash, then chlorine, then sodium hydroxide. So we have to go for the plant diversification, and we have to produce more and more products from the same brine solution. So that will lead to the more economic plant, and we can have the more products in an economic way. Then next we'll see the choice of the processes. So here the advantage of Solvay, that it can use the low grade of brine, then it consumes the less electric power, it will have the less corrosion brine, then no co-products to dispose of, then does not require NH3 plant investment. But the disadvantage being the higher salt consumption in this one, then higher investment in NH3 recovery units versus crystallization units for NH4Cl. So in this is modified solvent process, so that we are taking care of. Then with waste disposal of CaCl to brine stream, then more stream consumption. So these are the disadvantage of the solvent process.